Now this process does work even when the zeros are not actually integers. They could be fractions, but we need a bit of a workaround so that we can convert the zero that we find into factored form. So here we need to factorize this polynomial. They don't want us to graph it. They don't want to know what the zeros are. They want us to factorize it. But we have been told that it's got 3 distinct zeros, and it is a cubic curve. So that's the sort of maximum number of zeros that it could have. We can also see that the leading coefficient is 2, and the constant term is -3. Now, that makes me want to draw it up like this. It's got 3 distinct zeros, so I can tell that I've got 3 kind of sets of brackets, I suppose, to put my factors into. But this 2 out here is a little alarming because I'm thinking 2 times something times something times something has to equal -3, and 2 is not a factor of 3. So what's going on? Well, there must be at least one zero that's not an integer. So let's have a look at how we can use this same method to deal with it. We could use long division once we've found one factor, but we can actually persist with the trial and error if we want to. And the reason we can persist is we know that there's 3 distinct zeros. If we didn't know that, we might not be quite so persistent with the method. So I've put that formula into my calculator now, hit equals, and I've started by testing p of 1, and I found that 1 is a 0, and that means that x minus 1 is a factor. So let's go ahead and try -1 now. And that's not a factor. What would be the next normal thing that you might normally try if you're heading for something with a 3 in it? Rather than try 2 and -2, I'm thinking that 3 kind of makes sense right now. We want something with 3's in it. So let's try 3. And it's not a factor. How about -3? Yeah, -3 is a factor. So p of -3 equals 0. And that means that x plus 3 is a factor. Now I know I've got my leading coefficient right. I know there's 3 distinct zeros, so something has to go in here. And I can pretty much just use my constant term to work out what that needs to be. 2 times -1 is -2. -2 times 3 is -6. So I'm at -6 and I need -3. So what I need here really is x plus a half, don't I? To get that constant term working out right. So what to do? Can I leave it like this? Well, it's not wrong, but it's not best. When we factorize, we want to potentially, if we can, get it nice and tidy so that we've got integers here, if we can. So if we just rearrange this a little bit and put the 2, and then put this awkward looking factor next, and then we can put our other nice neat ones down. Now I think you can see that if we expand the brackets just here on this first set, then we've actually got 2x plus 1 there. And we can write it out like that. And that looks a lot tidier, I think. It's also a lot easier to confirm that our constant term, 1 times -1 times 3, yep, that's -3. And we can see that our leading coefficient would be 2 because 2x times x times x is going to give us the 2x cubed. So it seems fair to assume that the rest of these terms are just going to take care of themselves. Now you could always expand this out to double check that you get back to here. But if you've taken care of this and the right number of distinct zeros, there's not too much that can have gone wrong. Now in that last example where we saw that the factor needed to be x plus a half for things to work out, that means that the 0 was -1/2. And if you'd actually wanted to confirm that, we could have put in -1/2 up equals into our formula, and it would have confirmed that the p of -1/2 for that question was 0. So that's a good way to double check what that last term needs to be. Just make sure you're not mixed up between what the factor is and what the 0 is. Now, what do you do if you don't actually know how many distinct zeros there are? Should you keep going with that method that seems so nice and easy, using trial and error and the remainder theorem on your calculator? Well, you need to know when to stop. So again, we can use the leading coefficient and the constant to give us hints about when it might be seeming difficult, and we might have to revert to long division. So in this example, we need to start, as usual, by putting our formula in for our polynomial. So I've gone ahead and put the polynomial into my calculator. I've checked p of 1 and p of -1, and they both worked out. But then when I checked 2 and -2, neither of them worked. And since I'm aiming for -4, something seemed up to me. It didn't seem like things could work out. So at that point, I gave up, and I thought there's no point looking for more factors with that remainder theorem. I need to cut my losses here and actually go for the long division. Now, because I've got 2 of the factors, I could divide this whole thing by just one of these, but then I'm going to get a long cubic expression that I need to then divide by the other one. So instead, I've multiplied these together to get x squared minus 1 and reasoned that that must be the biggest factor that I've found so far, and that will help me find the factor that's also the quotient, making the quotient as small as possible, I suppose. So now there's going to be a few tricks in this because we've got x squared minus 1 here, so there's going to be a few gaps down below. So I can see that x to the power of 4 divided by x squared is x squared, but then when I multiply these out, I get x to the power of 4 and minus x squared, and I've lined the x squareds up there. Now when I do my subtracting, I've got 3 minus 1, so that's 4 of those, but I've got x cubed minus nothing there, so I've got x cubed. So I have this. Now I need to bring down my minus x. Now going again, x cubed divided by x squared, I have x, and when I multiply those out, I get x cubed, but I also get minus x. And that means that when I subtract these, I get nothing there. I can just write 0. But here I'm going to have 4x squared plus nothing. And now I've got my minus 4 down there. Now when I do this divided by this, I get plus 4. And multiplying these out, I get 4x squared minus 4. So sure enough, there's no remainders. So that means that this is my other factor. So now writing out my polynomial with the factors that I've found, I can see there that this is a factor, but I also knew that I had x minus 1 and I had x plus 1. So I can factorize my whole polynomial like this. And I can see that this section couldn't have been factorized any better. And I can tell that quickly because the discriminant b squared minus 4ac, which I get by doing 1 squared minus 4 times 1 times 4, is negative. So there's no solutions to letting this equal 0. So I can't factorize it any better. It doesn't have fraction zeros or anything. There just aren't any. So I saved myself some time by actually using the long division rather than going looking for factors that actually weren't going to be there. And lastly, what do I do if I know the number of distinct zeros? So I want to use that hack of using that remainder theorem with my trial and error for as long as possible. But there's no constant, so I'm not sure what smart choices to make. Well, here's a good example. We can see that there's no constant term on the end here, so we're feeling a little bit stuck. But if there's no constant, then it means that every term must have at least one x in it. So you can start by just factorizing and bringing the x out the front. Effectively, x equals 0 is one of the zeros. Now, what's left in the brackets is something that you can put into your calculator using your red A for the x's, and you can look for factors of 20 when you're making those smart choices.